Welcome to this video on variational calculus in classical mechanics. This is a movie which is part of a series that I've made for my lecture course on classical mechanics, which I teach to second-year students at the Technical University of Delft. My name is Jos Thijssen. In this movie I want to explain how a function can be minimized in the presence of a constraint, and then I will apply that to the Lagrange formalism, and that will enable us to find in an elegant way the constraint forces. So I hope you will enjoy the movie. We first consider variational calculus with constraints for ordinary functions depending on n variables. So first of all we leave out the constraints and we have an unconstrained minimization problem of the function of f depending on the vector of x, which is an n-component vector, and we find the minimum by taking the gradient of f. The gradient of f gives us a vector, one component for each component of x, and at the minimum, which I indicate by the vector x sub 0, we see that the gradient is 0 for each component. That's a standard variational problem. But now we introduce constraints, and these constraints have the following form. We require that the gk of x equals 0, where gk are functions also depending on n variables, and we have k of those. So k, the index k runs from 1 up to capital K, and that capital K is smaller than n because we don't want to have more constraints than dimension. And we assume, and we shall assume always in this movie, that the gk are independent constraints. Before turning to the solution of that problem, let us consider an example. Here I see a mountainous landscape on a map which shows me contour lines. So all these lines here, the brown lines, are contour lines which give me lines where the height is the same. So a brown line, every point on a single brown line gives me points of the same altitude. And now suppose I'm walking in this landscape along a path, and in this case I could for example take such a path, but let us consider this path here. And I'm asking myself, I'm not going to minimize, I'm going to maximize, but that's only a minute difference as far as the math is concerned. I'm going to maximize my position. So if I'm going in this direction, here is the mountain top. So in this direction I cross all these contour lines, so I'm going up. And here I'm going down. So in between there should be a point where I reach the highest point, and that's when I precisely touch this contour line. So if I exactly touch that contour line, I am at the highest point. Now the path, that is a constraint on my position. So the path constrains my position. So I can represent my path by such a function gk of x. So the fact that I'm on the red path gives me a condition like g is 0. And then I have an altitude function which is my function f, and I want to maximize that. And as we have seen, I can formulate the answer as well. The maximum height is achieved when the direction of the path is the same as the direction of the contour line at the point where I am here. Now I could formulate this condition also in a different way. What I could say is that the line perpendicular to the path is along the direction perpendicular to the contour line. A line perpendicular to the contour line is parallel to the gradient of f, and therefore we can say that the gradient of f should have the same direction. In other words, it should be proportional to the gradient of g, which gives me a line perpendicular to the path. And so this is the way to solve this problem. If we have more functions, so we have k larger than 1, then we would write this condition as follows: fx is the sum of all k's, and then for each k we have a lambda k gradient g k of x. So that gives me enough conditions to find the points where the path has reached a maximum or a minimum. Now we want to show this more formally. So suppose we have here the red path, which obeys gx is 0, and we take a point on that path. So let's take as the point x0, and we move a little bit away from x0. At x0, obviously gx0 is 0, because that should be the condition that x0 lies on the path. And if we move away a little bit, we come to the new point, x0 plus delta x, and we can do a Taylor expansion around x0, but if the new point also is on the path, then the result should be 0. And because already the g of x0 itself is 0, we find that delta x is perpendicular to the gradient of g of x0. Well, that's a well-known result. The gradient of g is has a direction which is perpendicular to the path given by gx is constant. Therefore, this dot product should vanish, and if we have more constraints that are imposed, then for each constraint this should vanish, and so we can write then this condition as delta x dot the gradient of g for each k taken at point x0 vanishes. Now we consider the variational problem for f within the subspace characterized by this set of constraints. And that means that if delta x is inside the constraint subspace, in other words, delta x satisfies all of these conditions, then we should have that f vanishes to first order in this delta x. And using the same Taylor expansion as we used there, this can be formulated as delta x dot gradient f taken at the point x0 should vanish. So what this says is that if we take any vector satisfying all these conditions, then it should also satisfy those conditions. And that can only be the case if the vector gradient of f taken at x0 is inside the span, it's a linear combination of the vectors gradient gk of x0. And that can then be formulated as the condition gradient f taken at x0 is a linear combination over all the k's, lambda k, gradient gk. And so the problem that we just described of the landscape, where we have only one constraint defining the path, is now generalized in terms of this equation. This can be neatly reformulated as follows. We define a new function which is capital F depending on x, and it's the function f we are interested in minus a linear combination with linearizing parameters, so those are the lambda k's, times all the constraint functions. And that what we then do is we first minimize this function capital F, so we take its gradient to be 0. And that means that we get a solution, and that solution depends obviously on the lambda k's that we have chosen there. So we have an x which depends on all the lambda k's, and that is the point for which this gradient vanishes. So we take that x, which is a function of all the lambda k's, we put it in all the constraints, and then we require that this x lies inside the constraint space, and that fixes the values of the lambda k's. And the lambda k's, they have a name. They are called the Lagrange multipliers. Sometimes people also call them Lagrange parameters. So let us consider a simple example. We have a function in 2 dimensions. It depends on x and on y, fx and y, and it's defined as x times y. And we have a constraint described by gx of y, and that is x squared plus y squared minus 1. And that should be 0 on the constraint, and that means that x and y are located on a unit circle around the origin, and so we need to find the minimum and the maximum values of f on that circle. So the function capital F is then defined according to the recipe that we have just studied as f minus lambda g, and I've put in here the values of the function f, x times y, and the constraint function g. And what we should then do is take the derivative of f with respect to x and with respect to y, and then put that to 0. That then leads to the following 2 equations. The derivative with respect to x gives me y minus 2 lambda x, and that should vanish, and the derivative with respect to y gives me x minus 2 lambda y, and that should vanish. So the first equation directly leads to y is 2 lambda times x, and the second equation leads to x is 4 lambda squared x, once we substitute for y what we found in the first equation, and we see from this that the solution requires, from the last line, that 4 lambda squared is 1, either or lambda is plus or minus 1/2. That's the only way we can solve that solution. Well, it turns out that in that case we have y is plus or minus x, and that means that the minima and maxima are found at the following 4 points: this one, that one, and that one, and that is to be expected because of the xy symmetry that we have in the problem. So in this case we didn't have to put in the solution back into the constraint in order to find the value of lambda, and therefore this is a particularly simple example of the Lagrange multiplier theorem. So now let us consider again the variational problem for a functional. In this case we take the classic functional of classical mechanics, which is the action which is defined as an integral over the Lagrangian, and we know that the first order variation of s with respect to a variation of the functions qj should vanish, and that translates into the Euler-Lagrange equations, which read d dt dl dqj dot minus dl dqj. That should vanish, and in fact this can be derived from taking explicitly a small deviation from the path, which is called delta qj. You multiply that by this. That's the first order variation within this integral, and we need a sum over j in front. So the term in the big parentheses can be considered as the gradient of L. So it's not an ordinary gradient which would give you the derivative with respect to qj and qj dot. The fact that these two are related, the fact that they are not independent, causes this to acquire the following form: one term per j and there is this d dt dl dq dot j. Now, if we interpret this indeed as the derivative, then we can generalize the arguments that we have derived above for the ordinary functions, and we can argue that this derivative should lie in the span of the gradients of the different constraints. And we assume that the constraints then only depend on the positions of the particles given by the generalized coordinates q1 up to qs. So let us consider the example of a particle moving in 3 dimensions, a single particle which is characterized by the vector r. In that case, this condition here translates immediately into this one, and here we have assumed that there is only one constraint. So let us now consider the example of a single particle subject to one constraint, which is given as g of r equals 0. In that case, this equation above immediately translates into this one, and we know that this first term here is the p dot, and then here we have a kind of force which derives from the constraint, and this one derives from the potential. So we can write this the applied force, and this should be the constraint force. But note that the constraint force depends on lambda, so we can solve this equation of motion, hopefully. When we solve it, it depends on lambda, and then we have to put it back into the constraint condition in order to find lambda. So the r depends now on lambda, and it is a function of t. And so to be specific, we could consider a pendulum which moves in a two-dimensional plane, x and y is taken to be vertical, and it's subject to the constraint x squared plus y squared equals l squared. So that should be put into the function g of x and y, which is x squared plus y squared minus l squared. That should vanish. So here is the picture. We choose y positive to be downward, and therefore we can immediately write down the L as m times x dot squared plus y dot squared over 2. That's the kinetic energy, and the potential energy with this convention for the direction of y takes on the value minus mgy, and L is t minus v, so we get a plus sign here. So if we try to find the equation of motion for x, then we first get from L obviously mx dot dot. There's no x dependence here, and on the right hand side we get a constraint force, which is lambda times dg dx, and that gives me 2 lambda x. We can do the same for the y component, and then we find from the kinetic energy the my dot dot. From the potential energy we get minus mg, and on the right hand side we get a constraint force which obviously has the same form as this one, but now with y. And so we can anticipate in this case that the lambda is smaller than 0, because the x will be driven back towards its equilibrium, towards x is 0. And we may also be tempted to solve this equation now, but then we assume that lambda is time independent, which it is not. So lambda is really a function of t. However, we can solve the equation in the small angle limit as usual, and in that case we have x is much smaller than L, but the force in the x direction will be a lot larger than the force in the y direction, and so that means that this quantity is a lot larger than mg plus 2l lambda y. And now we note that the y is approximately equal to L in this case, so we get an mg plus 2 lambda L. And in view of the fact that x is small, and that still this expression is a lot larger than the other terms, we can put this equal to 0. And that leads to the conclusion that lambda is given as minus mg divided by 2L. And we see now indeed that lambda contains the information about the length of the pendulum. And now we can put this, now this is time independent, so we can now indeed solve for x. And the solution that we find is that x is a cosine omega t minus t0, and the omega should be equal to the square root of 2 lambda divided by m. And putting this value for lambda in, and this should be a minus sign here, we get precisely the square root of g over L, which is a well-known result.